Hi everyone, today we're working on Module 1, Lessons 11, 12, and 13. And we're going to continue to look at how to use scientific notation in various operations. So Lesson 11 starts with the efficacy of scientific notation. And our learning objectives for today say, students continue to practice working with very small and very large numbers. And these are going to be expressed in scientific notation. Our second target says students read, write, and perform operations. Let's start with a scientific example because this is called scientific notation. And there's a very good reason, and that's because a lot of items in the science field are either very large or very small. For example, the mass of a proton is 0.0000000, so on, 1672622 kilograms, or 1.672622 times 10 to the negative 27th power. So what that tells me is that I would have actually had to write 27 zeros. The mass of an electron is 9.1093821 times 10 to the negative 31 power. Now, if we want to know how many times heavier a proton is than an electron, scientific notation is best because we don't want to be writing 27 zeros and 31 zeros and doing division with all of those digits. It's very complicated. You probably couldn't even type that whole thing into your calculator if you tried. So scientific notation is really going to help us out. So the ratio between protons and electrons is 1.672622 times 10 to the negative 27th over 9.1093821 times 10 to the negative 31 power. Now, if I multiply my numerator and my denominator by 10 to the 31 power, it cancels out that negative value in my denominator, and it gives me 10 to the 4th in my numerator. Now, this is based on my laws of exponents, multiplying powers, so this shouldn't seem very complicated. If I simplify 1.6 to 1.7 and 9.1 to 9.1, and then I say to myself, well, that's equal to 17 over 91. That's approximately 1/5. Not forgetting my 10 to the 4th power. When I multiply, it gives me about 2,000. So what that tells me is that a proton is about 2,000 times heavier than an electron. So even thinking about these tiny little pieces of an atom, that proton is still so much bigger than the electron. And so we really need to be able to make those comparisons and see how that could affect our studies. Moving on to lesson 12, we're going to look at the choice of unit that we're using. So my objective says, students understand how choice of unit determine how easy or how difficult it is to understand an expression of measurement, and also that students determine appropriate units. Now, you're going to get a cutout with two exercises, exercise 1 and exercise 2, that kind of explain why we would use a variety of units to represent certain scenarios. So that first one mentions that we're looking at a brand of MP3 player, and we're trying to decide how many songs that can hold. And it says it gives us about 1,000 songs, with an average song length being 4 minutes. So do I want the time of music that I have on my MP3 player to be represented by seconds, days, or years worth of music? So what is going to be most reasonable in terms of making that comparison? So looking at that blue text, it says that it makes the most sense for time to be displayed in days because numbers such as 240,000 seconds worth of music or 5/657 of a year is definitely more complex than just looking at 2.8 days. In exercise 2, we're looking at making cupcakes for the school fundraiser. And it says each cupcake contains about 20 grams of sugar. And the bake sale coordinators expect 500 people will attend the event. So assuming everyone who attends will buy a cupcake, does it make sense to buy the sugar in grams, pounds, or tons? Again, we can think about how many grams are in a pound, how many pounds are in a ton, and what would make the most sense in terms of labeling your units. Lastly, I just want to mention Module 1, Lesson 13, and those learning objectives. When we're interpreting scientific notation with technology, it is critical to remember that it's important how you enter those values into the calculator, and often the calculator is not going to be able to help you. It's not going to be able to hold the number of digits that you need. So we want to be mindful that we can compare numbers in scientific notation, and that we can physically apply the laws of exponents to interpret data and use technology to compute with very large numbers. So the technology might come in when we're simplifying coefficients of our scientific notation, not necessarily the 10 to the power, because that's going to give us very large numbers with lots of digits that we have to work with.